Imagine you want to build a spaceship. Any spaceship needs to do one thing. It needs to change its velocity. And the way we change velocity with rockets is we throw stuff out the back really fast. That's all a rocket does. We take some mass and we accelerate it backward, and by Newton's third law, the rocket goes forward. Simple, right? Now, a Russian fellow named Tsiolkovsky figured this out way back in 1903. He derived an equation. And don't be scared, it's just a simple equation, but it tells us something profound about rockets. The equation says that the change in velocity you can get from a rocket depends on two things: how fast you throw the stuff out the back, and how much stuff you throw out relative to how much is left. That's it. Let me write it out for you. Delta V equals the exhaust velocity times the natural logarithm of the initial mass divided by the final mass. Now, what does that tell us? It tells us that even if you double the fuel you're carrying, you don't double the velocity change. No, you get the logarithm of that factor. It's actually worse than linear. You get a logarithmic relationship. This is the fundamental tyranny of the rocket equation. Let me make this concrete. Say you've got a rocket that weighs 1 ton. That's your spacecraft, your payload, everything. And you fill it with fuel. How much fuel do you need? Well, in a typical chemical rocket, the kind that burns hydrogen and oxygen or kerosene, the exhaust velocity is about 4.5 kilometers per second. That's the speed at which the burning fuel comes out the back of the engine. Now, to reach orbit around Earth, just to get to low Earth orbit, not even to the moon yet, you need a velocity change of about 9.4 kilometers per second. Let's put that into Tsiolkovsky's equation. What mass ratio do you need? You need an initial mass divided by final mass of about 5 or 6. That means your rocket has to be 80 to 85% fuel. 85%, just to get to orbit. The whole structure of the space shuttle, the engines, the payload bay, all of that is only 15% of the total weight. The rest is fuel. And here's the beautiful thing and terrible thing about this equation. It's exponential. If you want to go twice as fast, the fuel requirement doesn't go up twice. It goes up exponentially. It's that natural logarithm in the equation that does this to us. So now let's think about going to the stars. The nearest star, Proxima Centauri, is about 4 light years away. Now, 4 light years is a fantastic distance. That's about 40 trillion kilometers. If we could travel at 10% the speed of light, which is incredibly fast by the way, it's 30,000 kilometers per second, it would still take us 40 years to get there. 40 years. And that's at 10% light speed. But here's the thing about going to the stars. You don't just want to cruise there at some speed. You want to get there in a reasonable amount of time. And you probably want to be able to slow down when you arrive so you can actually study the place, maybe land on something. Or if you're going on a manned mission, your astronauts would like to arrive alive and not as frozen corpuscles. So what velocity change do we need to reach Proxima Centauri in, say, 40 years with chemical rockets? Let me think about this. You need to accelerate for a while, coast, then decelerate for a while. The physics of this is interesting. You want to reach maximum velocity roughly halfway there, then decelerate the rest of the way. If you're doing that symmetrically, you need about half the delta V for acceleration and half for deceleration. The velocity you need for a 40-year journey, that's about 10% the speed of light, or roughly 30,000 kilometers per second. But here's the kicker. That's not your starting velocity. That's your final velocity. You need to accelerate up to that. The delta V requirement is enormous. We're talking about something like 50, 60, 70 kilometers per second or more, depending on exactly how you do the mission. Let's say 60 kilometers per second. Put that into Tsiolkovsky's equation. You need a mass ratio of e to the power of 60 divided by 4.5. That's e to the 13.3. Do you know what e to the 13.3 is? That's about 600,000. 600,000. That means for every kilogram of spaceship you want to get to Proxima Centauri, you need 600,000 kilograms of fuel. That's 600 million kilograms of fuel for a 1-ton spacecraft. That's insane. That's the tyranny of the rocket equation right there. Now, you could say, well, that's why we don't use chemical rockets for interstellar travel. Let's use something better, nuclear fusion or antimatter, or some really advanced propulsion system. And that's a sensible idea. Those systems can have much higher exhaust velocities, maybe 10 or 20 times higher than chemical rockets. But even if we had an exhaust velocity of 100 kilometers per second, and we don't, not yet, the mass ratio would still be astronomical. So people started thinking differently. Instead of trying to accelerate a manned spacecraft all the way to the stars, why don't we send little robotic probes? Tiny little things, much lighter, maybe thousands of kilograms instead of thousands of tons. There's a project called Project Daedalus. It was a serious study done in the 1970s by the British Interplanetary Society. They wanted to know, what would it take to send a robot probe to Barnard's star, which is about 6 light years away? And what kind of propulsion would you need to get there in a reasonable time? They came up with a design that uses nuclear fusion, not for a bomb, but as a propulsion system. You'd create controlled fusion reactions and direct the plasma out the back to push the spacecraft. The exhaust velocity in this system is something like 12% the speed of light. That's much better than chemical rockets. They calculated that you could send a probe that way and have it arrive at Barnard's star in about 50 years. Now, here's the interesting part. They calculated the cost. Now, Daedalus would have a mass of about 980 tons, mostly fuel and fusion reactors. The energy requirement, just the raw energy content of the fuel, would be enormous. They estimated that the fuel for Daedalus would have an energy content of about 6 times the world's total annual energy consumption. 6 times, in a single spacecraft fuel tank. How much would that cost? If we assume the energy would cost something reasonable to generate, and the Daedalus was built in the 1970s timeframe, the cost was estimated to be somewhere on the order of $50 billion for the fuel alone. That's not including building the spacecraft, the support infrastructure, the research and development. Just the fuel, $50 billion. And that was for unmanned probe. Imagine what a manned mission would cost. Now, people thought about this more carefully. Freeman Dyson, the physicist, addressed the economics of Starship construction. He said, okay, let's think about this differently. Maybe we can't afford this now, but economies grow. What if we wait 200 years until the world's economy is much larger? He estimated that if the world's economic output grows at about 4% per year, which is historical precedent, then in 200 years, the economy would be about 1,000 times larger than today. So something that costs 1% of the world's economy today would cost the same fraction, but the economy would be so much bigger that 1% would equal about 1,000 times as much money as the 1% of today's economy. The resources would be available even if the mission cost the same fraction of output. Dyson concluded that the first real interstellar probe missions would probably be built around the year 2168. That's about 200 years from when he made his prediction in 1968. Now, that's interesting, but I want to ask, is that right? Let me think about what the constraints actually are. You see, there's a clever idea here. What if you don't send all the fuel from Earth? What if you use a different kind of propulsion entirely? Imagine this. You build a huge laser up in space, or better yet, a laser beamed from Earth or orbiting Earth. And you have a spacecraft that's mostly a thin, reflective sail, like a sail on a ship, but it's being pushed by light instead of wind. Light carries momentum. When a photon bounces off that sail, it transfers its momentum, and the spacecraft accelerates. Robert Forward, another physicist, worked out the mathematics of this. A laser sail could potentially be accelerated to tremendous speeds, maybe even 20, 30, or more percent the speed of light, without carrying any fuel at all. The sail itself would be incredibly light, and all the energy comes from the laser, which is powered by, well, by whatever energy source you set up. Now, the challenge is building a laser system powerful enough and maintained long enough to accelerate the spacecraft. You need a laser with enormous power, maybe 65,000 billion watts, continuously for many years. And then you need to keep that energy beam focused on a distant sail. As the sail gets farther away, the beam spreads out. So you'd need an ever larger lens or mirror to focus it back together. Freeman Dyson estimated that setting up that kind of system, the laser, the power generation infrastructure, the focusing system, could cost on the order of hundreds of billions to trillions of dollars. Let me say that again, hundreds of billions to trillions of dollars. That's a lot of money. Now let's think about this differently. What does it actually cost to launch something into space? Right now, the space shuttle costs about $50,000 per kilogram to put something in orbit. A Falcon 9 rocket is bringing that down to maybe $1,500 per kilogram. That's still expensive, but it's better. For Daedalus, which weighs 980 tons, if we could launch it at $1,500 per kilogram, we'd be looking at 980 million kilograms times $1,500 equals $1.47 trillion just to launch the fuel into space. And that's assuming the fuel itself costs nothing. That's just the launch cost. $1.47 trillion. But wait, let me think about whether that even makes sense. Where would you get that fuel? The 980-ton Daedalus spacecraft would need fuel that weighs even more than that, because the rockets that launch it from Earth need to use fuel to escape Earth's gravity. So you're looking at multiple trillions of dollars just in launch costs. Now, here's an interesting thought. What if you don't launch from Earth at all? What if you mine the fuel in space? Asteroids have metals, water ice, everything you might need. If you could establish mining operations in space, extract raw materials, and use them to fuel your spacecraft, you wouldn't need to launch from Earth. You could assemble the whole spacecraft in space using materials that are already there. How much would that cost? That's harder to estimate because space mining isn't a mature technology yet. But in principle, if you've already got the infrastructure up there, the cost would be whatever energy you need to extract and process the materials, plus the cost of the propulsion system itself. One estimate I've seen suggests that if you have good access to space-based materials, you might reduce the cost of an interstellar mission by a factor of 10 or even 100. That would bring the cost down from trillions to billions, or even hundreds of billions. But here's the thing. Even that requires an enormous upfront investment in space infrastructure. You need to build mining facilities, refining facilities, spacecraft construction facilities, all in space. That's not going to happen next year. That's something that might happen over decades. Let me give you another way to think about the cost. An engineer named Andreas Hein did a careful analysis of what Daedalus-type missions would actually cost. He took into account the cost of the research and development, the cost of manufacturing the spacecraft, the cost of the fuel, everything. His conclusion? A Daedalus-style mission would cost somewhere between $100 and $200 trillion. $200 trillion. He said that would be economically feasible, meaning it's not impossible by the laws of physics, when it represents about 1% of the world's gross domestic product. Right now, the world's GDP is about $100 trillion. So 1% of that would be $1 trillion. According to Hein's analysis, at the current world economy size, we couldn't afford it. But if the world economy grows at about 3% per year, then in 100 years, it would be about 20 times bigger. In about 200 years, it would be about 400 times bigger. So when would a Daedalus mission be economically feasible? Around the year 2340, about 300 years from now. Now, you might think that's a long time, and it is. But remember, we've only been flying rockets for about 70 years. We've only been to space for 60 years. In another 300 years, who knows what we'll have figured out. But let's also think about cheaper missions. What about a smaller, less ambitious mission? What if you don't want to go to Barnard's Star? What if you want to go to Proxima Centauri, which is closer? And what if you don't need to get there and stop? What if you just need to fly by and take some measurements? For a flyby mission to Proxima Centauri, you don't need to decelerate. You can coast all the way and just zoom past at high speed. That cuts your delta V requirement in half. That makes it exponentially easier because of Tsiolkovsky's equation, that logarithm again. Freeman Dyson originally estimated that a smaller, simpler mission, a Dyson-class probe, might be affordable around the year 2085. That's more than 50 years earlier than the Daedalus mission. And there's another factor I haven't mentioned yet, technology improvement. As rocket technology improves, as we develop better propulsion systems, the cost per mission might go down. If we develop fusion rockets, or ion drives, or solar sails, those might be cheaper to operate than chemical rockets. So the timeline could shift. Maybe interstellar missions will be possible in 50 years, maybe 100, maybe 200, maybe longer. But the key point is, it's not physically impossible. It's just a matter of economics. It's a matter of wealth and resources. Here's something else that's interesting. The Voyager spacecraft, launched in 1977, are still transmitting data back to Earth right now. They're the fastest objects ever launched by humans. Voyager 1 is traveling at about 17 kilometers per second relative to the Sun. That sounds fast, but it's only 0.0057% of the speed of light. At that speed, it would take Voyager about 73,000 years to reach Proxima Centauri. But Voyager was launched with 1970s technology. We've made a lot of progress since then. Modern propulsion concepts could accelerate a spacecraft to 30 or 50% the speed of light. That would cut travel times down to a couple of hundred years rather than tens of thousands of years. And here's the beautiful thing about time dilation from special relativity. If you're traveling at close to the speed of light, time passes differently for you than for people on Earth. At 90% the speed of light, traveling to a star 10 light years away, you would experience only about 4.8 years of travel time due to time dilation, while 11 years pass on Earth. So even a journey that seems impossibly long to us becomes manageable for the astronauts on the spacecraft. Now, I want to come back to the fundamental question. Why is all this so expensive? What's the basic reason? It's the rocket equation. It's that exponential relationship between the velocity you want and the fuel you need. You can't escape it, not with reaction rockets, not with any rocket that throws propellant out the back. That's why everyone working on interstellar travel now is thinking about different approaches. Solar sails, laser sails, antimatter propulsion, wormholes. All of these are ways to get around the rocket equation's fundamental limitation. With a laser sail, the energy comes from outside the spacecraft, so you don't have to carry it as fuel. With antimatter propulsion, you'd get the highest possible efficiency. You'd convert matter directly to energy, according to E equals mc squared. You'd get more energy per kilogram of fuel than any chemical or nuclear reaction could provide. But even antimatter brings challenges. Antimatter is incredibly hard to make. A tiny amount of antimatter-matter reaction creates tremendous energy. Just 1 kilogram of antimatter annihilating 1 kilogram of matter would release energy equal to about 50 nuclear bombs. You'd need to contain it, handle it safely, and you'd need to have effective systems to convert that energy into thrust. It's theoretically possible, but practically, it's very difficult. Let me summarize what we know about the cost of interstellar travel. First, there are fundamental physics limits that we've identified using Tsiolkovsky's equation. These limits constrain how much fuel you need. Second, there are economic limits, what we can afford. Right now, it's probably not economically feasible. But as civilization grows and technology improves, it becomes more feasible. Third, there are technological limits, what we're actually able to build right now. We can build chemical rockets. We're developing nuclear rockets. We're still working on many of the more exotic systems. Fourth, there's what you might call the social limit. Would we actually choose to spend that kind of money? Even if we could afford it economically, would we? I think that last one is actually the biggest question. It's not really a question of physics or engineering or economics. It's a question of whether humanity will decide that exploring the stars is worth doing. And I think if you ask people, a lot of them would say yes. Humans are curious. We like to explore. We like to understand the universe. And the idea of reaching the stars, of finding out if there's life elsewhere, of visiting other worlds, that's something that appeals to people deep down. So I'll make a prediction. In 200 years, maybe 300, I think we'll have the capability to send unmanned probes to the stars. Maybe even manned missions, depending on what happens with life extension technology and so on. It won't be cheap, but it will be possible. And you know what? That's incredible to think about. Here we are, just 70 years after the first artificial satellite, and we can already imagine, we can already calculate how we're going to reach other stars. All because of a simple equation that a Russian gentleman figured out 120 years ago. All because we understand the fundamental principle. If you want to move yourself in one direction, you've got to push something in the opposite direction. That's Newton's third law. And from that simple principle, everything else follows. That's the beautiful thing about physics. It starts with simple ideas, simple equations, and then you follow them wherever they lead. And sometimes they lead to the stars.